Greetings sir and hello everyone. My name is Vichai Chan from the Department of Civil Engineering. This is a video from Math 132 Calculus-Term-Project. I'll be covering chapter 11. The section is going to be 11.1 is the parametrization of a plane curve. So let's look at the table of content for this video. So I'll be bringing up two important points from section 11.1, which is the parametric equation and cycloid, and after that we'll have some practical exercise. So first is parametric equation. So what is the parametric equation? Now, let's say we are given this curve, and you can see it bent upward and downward a lot. But we don't we can describe this curve of a function because it failed the vertical line test. You see that there are many points touching the line. So this is when we use something which is called parametric equation. This basically means that we're trying to describe the position of a particle on that line at a certain point in a certain time. In definition, if x and y are given as a function, when we are trying to write in a parametric equation, that means x would be the function and also y would also be a function. X would be f of t and y would equal to g of t over an interval e of that t value. So at that point, x, y would equal to come to instead ft and gt. Defined by this equation is a parametric curve. The equation are parametric equation for the curve. Now, we have to know that t is the parameter of the curve. Now, the variable t isn't always the parameter. Some excited will tell you that to use alpha or theta as parameter, and you have to switch two different variables. So, in domain E is the interval of the curve, and if E is a closed interval, let's say t is between a and b. If we plug a into both functions here, that means it will be the initial point, and b will be the terminal point. And when we give a parametric equation a parameter of an interval and its parametric equation, that means it is called a parametrization. Now let's look at the first example. Here they wanted to sketch the curve defined by the parametric equation x equal t squared and y is equal to t plus 1. The interval of t is minus infinity and infinity. So the first thing we can do here is that we can plug in the value for t. So if we plug in minus 3, that means x will be 9, y equal minus 2. Plug in minus 2 will be 4 and minus 1, and so on. If we try to plot all of these points, what we get is a parabola. Another way that we can do this is that we can eliminate the t parameter. So to do that, we take one function here. You can take x or y, but we take y because it is easier. We can solve it for t, then we get t equal 1 minus 1. See here in the x function, we also have t squared. So we can plug t into x. So what we get is x equals to y minus 1 squared. We can expand this, or if you remember the parabola equation, this is itself is a parabola equation. This might have h. H is that because this is a minus 0. So the second example is to parameterize the circle x squared plus y squared equal to 1. This is our circle. So if we try to solve for one variable, x squared plus y squared, this is not the correct way to do it. You see, when we're trying to solve one variable and substitute x equal to t, what we get is 2y function. And when we get this y function and we are trying to graph it, what we get is only 1/2. If we graph this positive square root, that will be 1/2. We graph the negative square root, it will be negative under half the circle. So it's not the whole circle that we get that we parameterize. So this way is incorrect. The correct way to do it is to remember the trigonometric identity. We know that x equal to cos of theta and y equal to sine theta. We can let theta equal to t, so then we get to cos t and then y equal to sine t. We can prove this is true by square both of them up. You can see here this is called t squared sine t squared, and what we get is 1. So the parameterization of this equation is x equal cos t and y equal to sine t. And to graph this is that we can start to plug the value of t from 0 until 2 pi. And here we're talking about a little bit into polar but not really into polar. So as I can see here, at t equal to 0, it would go into t over 2 and then pi and then 3 pi over 2 and went back to the origin. And the origin here is going to be 2 pi because it is one circle, so one revolution. Okay. Now that parametric equation is over, let's move on to cycloid. In cycloid, let's say For the pendulum clock whose bob, if you don't know what a bob is, in a grandfather clock you see that golden part in the middle or in any color, the round part that is called the bob. If it's spinning a circular arc, frequency would be dependent on the amplitude of the swing. But this wouldn't happen if the bob swing in a cycloid motion. You can see here, it basically means a circle that travel around the line. Now, let's see this visually. So let's say a wheel with a radius of alpha is rolling along a horizontal straight line. We define the parametric equation of the path traced by that point P on the wheel's circumference, and the path is called a cycloid. This is what a cycloid path is going to look like. As you can see, we are tracking a point on that circle as it spins around. What we get is similar to a half oval shape, and many of them, they seem to depend on the interval of what we set for it. So how do we find a parametric equation for this? So the first thing we can do is that we can take the line and we can set it as the x-axis. Then we take the angle t as the parameter. We know the wheel center would be lie at AT and A. And according to P, to find it, we know that this length from 0 to M is the time that it takes from it to spin to here to here. So this is AT. And then you can drop a line here, this will be cos theta, so it will be AT plus cos theta. We know the radius is equal to 2R or 2A. So if we try to drop a line on the y-axis here, then it would be A plus A sine theta. Now to describe the theta as our parameter, we need to look at how this thing moves. This thing is moving a clockwise direction. So we know that if you recall from our previous visualization, we know this is 0, this is 2 pi, this is pi over 2, this is pi, and this is 3 pi over 2, and we bet here it's going to be 2 pi. So we know that from this angle to here is going to be 3 pi over 2. So that means that t plus this angle theta, we get 3 pi over 2. We can solve for theta, and substitute it into cos theta and sine theta. For cos theta, substituting it using the formula of trigonometric identity, we'll get minus sine t, and same with sine theta, we'll get minus cos of t. So this means that we can plug this into our P equation here. So the equation of the cycle will be x equal to AT minus A sine t, y equal to A minus A cos theta. We can also get A out of here as well. Now the cycle is over. Let's move on to practice exercises. So the first exercise is to find the parametrization of a line through the point AB having slope m. So immediately, the first thing we need to do is that we need to find the equation for the slope. So slope is going to be m equal to the initial minus the terminal point. So that means we can get this equation here by throwing x minus a to the m side. Okay, now that we have that, we can set our parameter to equal to something. Let's set it to x minus a. Once set to x minus a, our equation became much simpler. Y minus a is equal to mt, y minus b is equal to mt, sorry. So now that we have that, y would be equal, we can solve for y, and y would be equal to mt plus b. We can solve for x, and this is the parameterization of the line. Another way to do it is that we can just let t equal to x itself. Once we get that, we can see that the equation will become y minus b equal to m times t minus a. So we can solve for y, and what we get is another parameterization. This one is also the same as this equation. We try to eliminate the t parameter, what we get is this same equation. So both ways correct. Now, second example, we define the parameterization of the circle starting at the x minus 2 squared plus y squared equal to 1. The starting point is going to be 1, 0. And moving clockwise once around the circle. Remember guys, we are moving clockwise. Using the central angle in the accompanying figure as the parameter. So what I want to do is that I want to use this angle theta as the parameter. So we don't have to substitute any t. Now, to do this example, first we have to drop a line down here to get a right triangle. Now we know that a circle parameterization would be a cosine theta and y equal to a sine theta, just as trigonometric identity. Now our y here is equal to sine theta, and for x here, we see that if we drop this, this is only this much distance, or there's more, like 2 distance more, so that means x will be equal to 2 plus cos of theta. Now, once we get that, that is itself the parametrization of this curve, of this circle. We don't need to do anything else, as they tell us that theta will be the parameter. So the final example is to find the parametrization of a line segment joining point 02 and 40 using the angle theta and the accompanying figure as a parameter. Again, this is going to be our parameter, the angle theta. So to do this, first, we're going to also drop a line down here to get a right side triangle. Now, I want to remember that tangent, it will be equal to the opposite over adjacent. This is our opposite, this is our adjacent, this is our hypotenuse. So our opposite will be y in this y graph, in this y plane, and our x will be adjacent. So we know that tangent of theta will be equal to y over x. We can solve for y. Now, for the point slope equation, as we know here, this is a slope. So it will be the initial point minus the terminal point. So we get the slope of minus 1 over 2. Then again, you can plug it into another slope formula, which is the term we're trying to find is here. So we're going to be initial point minus the terminal point, or minus the terminal point. Now, once we get the y equation, we can replace y with x tangent of theta, and then we can solve for x. What we get is x equal to 4 over 2 tangent of theta plus 1. Now when we get x, we can plug x into 1. 1 is our equation. We set it equal to 1 so that it will be easier when to write it again. Now, once we plug x in, we can solve for y. Don't forget the 4 tangent of theta over 2 tangent of theta plus 1. And this 2 itself, the parametrization of this slope line. So, this video has come to an end, and I would like to give you guys one important quote, which is that you have to remember that life is like a math. If it goes too easy, that means you are doing something wrong. So thank you guys for watching this video. Thank you, Mike, for spending your time watching it, and have a great day. Thank you.